Welcome to EDU World Space.
Okay, so in this problem, you have a cube sliding on a surface and it hits an obstacle, cube tilts. So we want to get the minimum value of V such that it falls over the table. And then we want to note also that there's an elastic collision that's going on. Interesting. So let's get down the givens and then we can discuss how to do the problem. And I'm also going to pull up the picture. Oh, fine. And so interesting. And we want it to fall over the edge and not just sort of get hit. And so we want that minimum velocity. So I suppose so at some point it's gonna, if it's a low velocity, it's just going to hit, rotate a bit, and then rotate back. And if it's a high velocity, it's going to hit it and then fully tip over. And so, yeah. So I'm thinking is at what point really does it like actually fall over? And I would say if you get this block to go from like its center of mass being here, then it hits the thing, and then it at the end of the table, what do they call it? Obstacle, and then it hits the obstacle. I would say if this rotates sort of from here to here, let me draw a better picture of that. I'm basically, if it ends up on one of its edges, then I would say that it would flip over. So we need to find when that would happen. And so let's figure out if we can use a conservation law. So we can't use we can't use energy because there's an inelastic collision. But let's see if we could use any kind of, what other equations? So, I mean, momentum in this system, I would say, is probably not conserved because the table itself is probably not on a frictionless ground. So I don't think we can do linear momentum. Let's think about angular momentum. So as it hits here, it's producing a force that is basically to the left. And R is this way. So it actually is producing a torque. So we can't really, I don't think we can really use any conservation laws, but I think what we can do is say, we can say torque is R cross P. Or sorry, R cross F. And we can set that equal to I alpha. And then we can talk about a rotation here. Oh, actually, if you think about so I kind of take back my lack of angular momentum conservation because sure, there's a torque about this axis, but there's not a torque about the axis of rotation on the corner, right? Because the force is being applied at the corner. So then there's no torque about that axis. So then you can actually say the angular momentum about this axis is conserved. So might kind of put this to the side. So I'm thinking of it like you initially have some angular momentum about that axis through the corner. So here's the corner, and then here's the velocity, and here's your r. That has a non-zero cross product. So that's your initial angular momentum about that point. And then as you rotate around this, it translates to the block, this point being fixed, and then the block rotating. So I think we can use that to answer the question. So we can say L initial is L final. And again, it's all about this axis of rotation. So the initial angular momentum is going to be mvr. So mv times r perpendicular, of course. And the part of r that's perpendicular to F is going to be half the length of the box. And then we know that the box is of with 2a, so it's going to be a. It's already kind of a good sign that they gave us 2a. So that's the initial angular momentum. And then the final is going to be the moment, the I times omega of the cube. So I need to get the moment of inertia of a cube. So I'm going to look that up. It's certainly not something you would be expected to derive in the problem. So I have what it is around the axis of rotation, or around the center. So that's 1/6 m times 2a squared. So just trying to make sure we're on the same page, I'm trying to find the moment of inertia of a cube about this point. This is 2a. And then I about the center point, so I'll call that IC, is equal to m times, m over 6 divided by 2a squared. And so that's 4 over 6, so 2 over 3 ma squared. And then you want to multiply, you want to add the distance between this and then the new axis. So what is that distance? I'm going to draw this cube a million times. So this distance, so if this distance is 2a, this is just 2a times the square root of 2. And then half of that is going to be this divided by 2. So it's just going to be a square root of 2. So we can say I about the corner. So I don't know what to call this. I'll just call it I. IC is about the center, and I is about the corner. And so you can say I is equal to IC plus m times this distance squared. This distance is squared is a squared times 2. That, again, that's through the parallel axis theorem. And then we can add these two. So we have ma squared times 2/3 plus 2. So that's 6/3, 7/3, 8/3. It's 8/3. Doesn't this all seem fake at this point? Okay. And so now we can get the initial angular speed as a function of the velocity. So we know omega is mva divided by I. So you can do mva divided by our new I, which is ma squared times 8/3. So times 3/8. The m's cancel and a cancel. So you have v over a times 3/8. And now we can use energy conservation. So this is the initial omega. And then as it rotates up, we want it to have 0 speed when the center of the box is directly over the obstacle. So let's draw like a nice, careful picture of what's going on here. So this is going to rotate up. So its initial height is just going to be A, and then what is its final height going to be? Oh my God, I love problems with just tons of geometry. That was not sarcastic. I actually really do. So this new height, like we said before, was A square root of 2. So then the change in potential energy is going to be mg times the change in height. So then that's A square root of 2 minus A. And then, so you can say 1/2 I omega squared is equal to mg times A square root of 2 minus 1. And excellent. So now we can just sub in a bunch of stuff. So let's sub in for omega, and we can sub in for our I. So let me go ahead and do that. So that's 1/2, and then I is A squared times 8 divided by 3, and then omega is V over A times 3 divided by 8. And we're going to square everything because it's omega squared, and that's mg A square root of 2 minus 1. And now we can simplify. So let's kill off one factor of this. We can kill off this A squared. We can kill off this M. And now let's see what we get. So this is looking kind of messy. I'm just going to rewrite it. 1/2 times V squared times 3 over 8 equals G A square root of 2 minus 1. And you got V is equal to square root. So that's 3 over 16. Bring it over. 16 over 3. A G times the square root of 2 minus 1. Wow, that's actually the same as somebody else did this problem before me, or for some reason an answer is in front of me as I type this, and it actually is the same. So it's always funny when these sort of complicated processes actually work. It's very satisfying.